Good day. I was afraid to say good morning or good afternoon. I don't know when this is going to be shown, but good day. I'm Bill Hopwood. I work at the Oak Ridge National Lab. I'm going on 45 years now. I have a BS in chemistry and an MBA in industrial management. Started at Y12, and first third of that career I was working in the analytical laboratory. The second third of my career I was managing the MC&A department at Y12. And then for the latter part of it, I've been working a lot of the international programs, especially the mp4 program, Material Protection Control and Accounting. The DOE, Rosatom, the U.S. and Russia have a lot of exchange programs going on to protect nuclear materials and facilities. And it's in that arena that I want to at least try to give you a feel for MC&A and what it means. Some of you have probably been around nuclear materials, and it may be second nature. When you talk about nuclear materials, there are a lot of different kinds, and we'll get into describing some of those and the sensitivity of some of those. I think maybe to put a little bit in perspective, this is a plaque that's been around for many decades here in the Oak Ridge area. And in essence, if you were to take that geometry of U-235, fully enriched, say if that were uranium metal, U-235, that's equivalent to 1 million pounds of coal. So you can see why that kind of material is very expensive, and it's also very risky. We don't want to lose it. So given the idea that we want to protect it, maybe you want to pass it around. You want to protect it, and you want to account for it, and there are all kinds of things that are required to do so and be proper with it. So let me just start talking about the evolution of MC&A. You've probably got a lot of different ways that nuclear materials may have a meaning to you. Some of you, it may be radioactive materials, and there are a lot of controls when you're dealing with radioactive materials. Some it may be related to various research activities in hospitals and or universities that are dealing with radioisotopes. In the DOE and the nuclear fuel cycle that I've worked with, and also what NRC is handling, it has a different meaning when we talk about nuclear materials. And the materials we're dealing with, in essence, came into being predominantly during World War II as part of the Manhattan Project. The effort to try to beat the Germans in potentially coming up with a weapon that could be using nuclear material. In the Manhattan Project, it was established in the 40s. 41 is when it really got started. There were 3 predominant locations that were working with the nuclear materials. Los Alamos, where the weapons design and the assembly and the testing was worked with. Hanford, where plutonium production was being done. At the Oak Ridge National Lab, where we work, there is a prototype that was done for the Hanford reactor. We have the graphite reactor that is now a historical site. And in essence, the prove-in was done there before the Hanford reactor was finished. The Oak Ridge sites also were involved in enriching uranium in U-235. So it's the start of the nuclear materials and the concerns that we have were during this period of time. After the war, there were then moves to make sure that materials were contained, controlled, protected, and the United States passed the Atomic Energy Commission, which set up first regulatory basis for a lot of these. Up until that point in time, it was mainly the value of the material and the cost that it took to separate it. But now you have the concerns for proliferation in the early stages. We want to make sure that there's peaceful use of these and that we're controlling what we have. And so the Atomic Energy Commission came into being. It eventually evolved into what we now know as the Department of Energy and the Nuclear Regulatory Commission, the DOE and the NRC. Early on, again, it was financial accounting just because of the cost that it took, and a gram of enriched uranium, U-235, and or plutonium that had been separated was extremely expensive. So a lot of the early accounting systems that were set into place were because of the actual value of the material. During the Cold War, as a lot of the sites, number of sites increased, activities, the amount of processing that went on, certainly it started evolving. There was the competition we had during the Cold War. A lot more materials were fabricated and in essence processed and handled and reprocessed. There was the concern for material losses, not only for the financial part, but also for proliferation part. Where are they? How much do we have? And then environmental releases, certainly in the 70s and 80s, as all of the impacts. So there were a lot more increases in regulations put into place to keep track of these materials. And then, of course, as we've seen in later times, probably started, I think, with the Munich games in the 70s, were the first times that terrorists, in essence, took hostages and threatened so many people and held the world at his attention there. It was after that that I started seeing a lot of the upgrades at Y12 where I worked, a lot of the material access area controls and all of the different regulations and systems that were put into place. So there's a lot of evolution that's gone on. And certainly since 9/11, we've seen another push to make sure that we're handling these, controlling these, minimizing the amounts of them scattered around the world. So after the Cold War, it's all of the different countries that get involved with nuclear materials and then have economic difficulties. Are they protecting them the same way? We got heavily involved in helping countries with that since then. A lot of the at-risk materials that could be out there with various agreements to take weapons apart, to reprocess the material and track these and make sure that the agreements are being met. And the growing threats from terrorism, as we've mentioned. A lot has also changed in that a lot of facilities have now been decommissioned. The materials have been located at other places, reprocessed, disposed of. So a lot of downsizing and reconfiguration has gone on. And that's been a driver as to how we keep track of the materials and measure them. And then again, meeting all the environmental safety and health compliance issues with it. An MC&A program has several components and reasons that it's in place. The primary reason certainly is the accurate accounting, to be able to keep track of it to grams, sometimes micrograms with some of these materials. But to make sure that we are keeping track of it for non-proliferation purposes, safeguards purposes, and as well because they're driven to be so accurate with them or responsive as to where the materials are. They're the basis for a lot of the financial accounting systems. There's still extreme value to these materials and cost a lot to either produce and or keep track of or dispose of. So most of the financial accounting systems are based on the MC&A accounting systems because of the need to measure these. We need to have timely detection, not only to be able to respond, but also have a robust system that says, I'm going to deter anybody even trying to get a hold of this. And then we want to provide, as far as the MC&A system, one component of the overall protection systems that are in place. There's a lot of integration that goes on between MC&A and the other organizations that are trying to make sure materials aren't lost or being protected and nothing of concern. The two predominant agencies in the U.S. that keep track of nuclear materials, certainly in the Department of Energy for all the government-owned materials, weapons production and research that goes on at these facilities, and the material in essence being owned by the government, as well as the facilities that are owned by the DOE but managed by different companies. In the private side of it, the energy side of it, the NRC is responsible for coming up with the regulations and requirements and all of the agreements that are made with facilities that have nuclear materials. Basically, when you get into the weapons production and there are those facilities as part of DOE, once it's turned over to the military, that's their own accounting system then. But all of the records are there so that when any of these are decommissioned, brought back, or reprocessed, or the material is converted for some other use, all of the accounting around that still exists in the DOE systems so that you can put all of the values together and understand what's happened with it. Other countries that I have at least been able to visit or the opportunity to visit have at least one or two agencies and sometimes more that are keeping track of these materials. And then if you have agreements with the International Atomic Energy Agency, you're going to have some MC&A requirements there. There are probably some additional things that they'll want to control and keep track of, and data sets that they're interested in. But by and large, it's depending again on the robust MC&A system and the protection systems that are in place at these sites that have agreements with the IAEA. There are a lot of terms in MCNA, just like any discipline. One time I scanned the glossary, and so there's over 500 terms that are in essence specific to MCNA or have meaning. It's not to say they may not be in other disciplines as well, but at least if you start getting into it and understanding, communicating, and trying to live up to the regulations, you'll run into over 500 terms. I'm just going to give you a few here that I want to get into a little bit more detail that hopefully you can see what comprises an MCNA system. I grew up with NMCNA, Nuclear Material Control and Accounting, but you run into the MCNA, you run into the reverse of it, MAC, Material Accounting and Control. When you look at safeguards and security regulations and orders, the safeguards is typically the part of it that's covered in the MCNA. In the major program that we have with the Russians, where we have exchanged back and forth, it's called the MPCNA. The MCNA part of it, but it's Materials Protection, Control, and Accounting. Nuclear material. And nuclear material is not radioactive material. It's nuclear material that's of concern as far as being able to propagate or needing non-proliferation needs built around it, because we don't want it misused in a nuclear device. So we'll have certain nuclear materials that I'll show you a table of those. Special nuclear material are those that can be used directly in either U-235 or plutonium in a device, and you'll see that broken out again. So special nuclear materials are a different category, a more sensitive category of nuclear material. Material balance areas. Wherever the material is, we want to be able to say that we know how much we've got, we know where it is. When it transfers out or transfers in, we're accounting for it. So in some form or fashion, you're going to have a bound that will tell you how you keep track of these materials, how you report them, how you measure them, how you take inventory. So material balance area, MBA, you'll see that a lot. And book inventory, just like a bank. They've got inventory records for all the money that they have available in their bank. We will have a book inventory that represents all of the accountable nuclear materials that are listed in that MBA and in that overall facility or site. So there is a book that has everything listed. Somewhere along the line, you've got to check and make sure that what's listed in the book and what you have agree. That's why you take a physical inventory then. You go out in some set time, whether it be monthly, bi-monthly, semi-annual, or annual, depending on the sensitivity of the nuclear material. You're going to take a physical inventory, and you're going to compare that with your book inventory. And if you have discrepancies, you've got to work on resolving that. Why? And typically, if you've got material that is item-specific, nothing changes about it, you're probably not going to have a difference between what's on book and what you find when you take physical inventory. If you've done processing, I think you could imagine, take a bank. They were to take all of their money, convert it all to pennies, take all those pennies and chop them up and dissolve them all, and then go through a process to reprecipitate and convert them back to metal and make the pennies again. You think they're going to have the same number of pennies? No. And we're not in a processing facility. When you go through that kind of detail, operations, conversions, and everything else, you're going to have what we call an inventory difference. ID is what you will see when you deal with DOE facilities. If you deal with the IAEA or some other facilities, it's called MUF, Material Unaccounted For. Politically, that didn't sound good several decades ago. We'd rather call it inventory difference than material unaccounted for. So DOE adopted the inventory difference. But it's the difference between the book inventory and the physical inventory that you've taken. And there are all kinds of limits that's got to be within. Knowing that it won't be zero unless you have an item type inventory, then it's got to be within limits. And those are based on a lot of different components that make up the value, measurements, and sampling and things. Same thing for material that's transferred between material balance areas or facilities predominantly. If you have Los Alamos ships material to Y12 or Oak Ridge ships material to another facility, ORNL does, you have to have material measured on both ends, because most sites don't measure with exactly the same systems, measurements, the different analytical methods or different sampling techniques. So you may have a ship or receiver difference. Again, that's an inventory difference, but it's between what happened with the material shipped from one and received by the other. And so it has to be within limits. And then because there are about 15, 16 different nuclear materials, and they're not all the same threat or sensitivity, there's got to be a graded approach. You cannot guard all nuclear materials and protect them to the same degree. And so you've got to have a graded approach. So these are the terms that in the rest of the presentation I think that you will see come out. And hopefully I will be able to give you enough feel for it. These are the accountable nuclear materials that are under the DOE requirements. You'll see on the left the S&M, the special nuclear materials. These are the ones that in the right concentrations and quantities and configurations could produce a nuclear device. And so those are the most sensitive and the ones that will build the most protection system around and the most material control and accounting systems around. The other that you see there are source materials. Typically they can be used to make or produce the special nuclear materials. So they are from point of time till you first get them to the point that they're disposed of or whatever process they went through, you're going to keep track of them to a certain degree. They aren't a threat in themselves, and so they don't need the same protection as the special nuclear material, but you want to know who's got it, what are they doing with it, are they using it as a source material to make these others. And then you have a lot of other nuclear materials, and you can see that most of those are radioactive materials, some fairly highly radioactive materials, but they are related to the nuclear weapons cycle in various forms and fashions. Sometimes they're used for different enhancement aspects, but they are kept track of to very small quantities. Again, they're very expensive, and it takes a lot to produce a lot of these. A lot of them are used in nuclear research and nuclear studies, and so you may be familiar with some of them. So those are the ones that, in essence, are required by the Department of Energy to be protected, and basically the same ones you'll see in the NRC. They just won't typically have all of these. And so you're going to build your MC&A and your protection systems based on these and on some graded approach. And that's what this table does. You can see on the left column there, you're talking about the purity of the material. You're talking about how attractive is it. If it's a weapon, that's the highest attractiveness level. We don't want someone to run into a facility and steal a weapon. Okay, you can see that one needs to be right on the top. So that's A. Typically, when you fall down from that, you don't have, you know, an assembled weapon or something like that. You're down to pure metal. You're down to maybe components. And so we give those a fairly high attractiveness level, B. Then you fall down to pure materials, but they're typically compounds of either plutonium or uranium. And so it takes more to process, develop a weapon out of that. So it's not as attractive as the ones above it, but it still has, you know, the right amount of quantity and the right approach, which somebody can do some processing in their garage if they want to. So you, in essence, do want to give it a fairly high attractiveness level. You get down to the low-grade materials. Those, it takes a tremendous amount of processing to get to the point that you have material that could be of concern. And then you have those in Category E, which probably a lot of sites wish somebody would steal those. It costs too much to even keep track of and process, but I got to. But anyhow, you have the attractiveness levels that are added to these materials based on how easy they can be converted. Then across, if you look at plutonium and U-233, which both of those are pretty equal in the amount of material that it would take to make a nuclear device, it takes, in essence, certain quantities in which you get then to a Category 1, 2, 3, and 4. And so you notice that the quantities go down as you're talking about a lower category, 2, 3, and 4. You notice that if you look at the plutonium, if you got greater than 2 kgs and greater of plutonium metal, we consider that Category 1. And if you want to put the attractiveness on it, it's 1B. That, in essence, would get defined in, if you've got that kind of material, in the regulations as to how much protection you build around it, all of the different components and things that you build into it. So we can't protect all materials to the same degree, so we've got to break them down as to attractiveness and quantities and categories so that we know how to put our limited amount of money for the right protection. So as you go down and as you go over to the right, you'll see that you fall in essence to larger quantities to make a Cat 1. Once you get down to D material, you can't even get enough to make a Cat 1 for plutonium. But you can use that table to start, in essence, projecting what kind of material you got, what kind of systems you have to build. As you switch over to U-235 on the second half of that table, you see it also has Cat 1, 2, 3, and 4. But you notice it takes about 2.5 times as much of U-235 to be as of concern as plutonium. But nevertheless, facilities that are handling a lot of uranium and a lot of enriched uranium and a lot of highly enriched uranium, they can get to be Category 1, 2, 3, and 4. In our typical facilities for Cat 1 and 2, you're going to see tremendous safeguards and security built around it. If you ever had a chance to go down Bear Creek by Y-12, you'll notice it's a lot different than going down Bethel Valley by ORNL here. And so you can kind of get a feel for the differences in the categories of material and what it takes for protection. Those kind of reflect what it takes for the MCNA and how well you have to know how much it is, how well you characterize it, how well you account for it, how often you take inventory. So those also are a reflection and are guided by the DOE orders and directives as to how we have to build it. In case some of you haven't been in any processing areas or seen a lot of material, just to give you an idea, the picture on the left on the top, that's just a lot of different types of materials you might see in a uranium processing facility that's actually fabricating metal parts or components or things like that. That hand in the bottom is holding 4 kgs of 93% enriched uranium metal. And above it you see in the bags, when you get it to a facility like this, it's handling that high enrichment material, you collect everything and recycle it and reprocess it. Even if it's got gram quantities in it, and that's 93% enriched material, you've got to account for it. You're probably going to reprocess it because it's so expensive, but if nothing else, you've got to measure it in those different bags and items and containers. The bottles there are just showing you typical pure compounds of uranium. The one on the top right, that's a safe way to store a lot of highly enriched uranium. That's about 19 kgs of 93% enriched uranium metal. And you notice it's a hollow ring. So they have a tremendous storage facility, vaults, access controls, and everything. But this is a good way for criticality safety as well as the protection of it to store it and take inventory and know what you got when it's necessary. Underneath the bottom picture on the left, just different standards that you may have for uranium or other nuclear materials in which you may calibrate instruments with it. It may be you're just doing a confirmatory, we call it, check, in which you're checking enrichment, and yet you want to make sure that if you've got programs that require calibration and or checks for measurement control, that you've got something to compare with. It may be that you use some of these standards to put in containers if you've got some type of counting system that is going to measure the amount of material in drums like you see to the right there. Those of you that have been to maybe the ORNL Safeguards Lab, you've probably seen a lot of these standards and items that are measured. So give you a feel for the different types of materials and shapes and configurations you may run into. There are a lot of basic elements that an MCNA program has to have, and it's spelled out in the directives. And in essence, depending on the site, the category of the site, if it's 1 or 2 category site, then it's going to have tremendous amount of detail requirements that are broken into different plans and procedures and when it's implemented. But the basic thing is to take the requirements, looking at your materials, what your inventory is, and coming up with an MCNA plan. How are you going to implement? How are you going to protect and spell it out? Not only so you build it appropriately, but when there are inspection teams coming in, they're going to go to the MCNA plan to start with and find out if you built it the way you said you were going to build it. A lot of the approval you may get to handle materials and operate may be that this plan has in it what it needs to be. It's something that's interactive as well with the DOE, either the local office or headquarters, that you in essence, they'll review your plan and they're satisfied with it or not. So there's a lot of upfront planning and defining and spelling out details before you get to handle these materials. And then you put the plan in place and you live up to it. A lot of details behind it with all the procedures that may be necessary in the support organizations. The operations areas will have procedures that break down all these details to do not only whatever their processing is, but how they include MC&A into what they do. Again, it's the graded safeguards approach based on the attractiveness level and the quantities and the categories. You can't do it all. So you would break down each one of these types of materials and say to what degree and how you're protecting those. The accounting systems. If it's not a large facility, limited amount of material, and maybe MBAs, you may just have a manual system. You may handle it with ledgers and log books and keep track of your inventory that way. Make changes to it on paper. If you've got a fairly large facility, a lot of material and a lot of activities and processes, conversions, shipments in and out, then you're going to find that an automated accounting system, fairly large computer-based system to do this with, to give you what we would call typically near real-time accounting. And it also helps reduce a lot of human errors that can work their way into an accounting system. You'd be surprised how much time you may spend because someone put the wrong decimal place or put the wrong number somewhere or put the wrong analytical value for this one with the wrong sample with the wrong part. So the more it's automated and will double check for you and make these transactions, the better off you are. The accounting system itself, it needs to reflect, you can't be absolute. That's the reason we call it near real time. Real time's a tough one. Well, maybe you got all kinds of tags and sensors and real time that somebody moves it. I know they've moved it. But most of the time with the accounting system we'll refer to as near real time. But you want to be able to, within a given period of time, and that's usually defined by DOE as well, based on the material, where is it? How fast can you find it? Hopefully if you've got other control items in place that say an alarm is going off, you're responding quickly too. And then you balance that to the accounting system. You've got to spell out all of the measurement systems. Everything that is there has got to be on a value that's defensible. So you may have a lot of different measurement systems, and I'll get into showing you a few of those. The material containment. This is where a lot of the times between operations, MC&A, and the physical protection, it's well defined where this material is. It's inside a certain gate, fence, building, vault. And you're going to have where it's contained. It may be inside containers that are welded. It may be in containers that have tamper indicating devices on them, maybe electronic or paper. But in some way or another, you've got to have it contained. And in essence, it's where it's supposed to be as well with that system. The access to these materials, where they are. And I'll show you a chart a little bit later on that how you get further and further from the actual material that's the target and how many layers of protection you have built around it, not only in the physical protection but keeping track of it. Material surveillance. There are a lot of different ways that, in essence, you would keep your eye on who has control, who has access, what are they doing with it. CCTV, you'll see a lot of cameras that are set up in places. You may have requirements for no one person can be in there alone. There may be multiple person requirements that are allowed to get into a vault, maybe even more if they're processing or handling it and it can actually get at the material. It may be you required in a glove box that no one else can get access to and you're working at it through these boxes. So there's a lot of different ways that you may have it contained, and you have surveillance mechanisms that tell you, yes, it's there, or something happened and we got to respond. Then again, depending on the category of material and how much you have, you're required to take physical inventory periodically to balance with your book inventory, as we were talking earlier. And that gets defined by the DOE, and so you will set up all of the processes that it takes for taking inventory. And that may be, if you're looking at a site like Y12, that may be several days. It may be a few weeks by the time they take samples and analyze those and get the results back. So, you know, whether it's a day or several days or a few weeks, then you've still got to take complete recalculation of the inventory you got to compare it to the book inventory. So, and depending on the facility and the amount of material, it can be simple or very complex in taking physical inventory and spelling that out. And then all the control limits like we were talking about. And a lot of that, as we get into a little bit more, I'll describe for you some of the uncertainties that go into it that you have to take into account. We'd like to think we can measure something exactly, but it's not true. You've got uncertainties around any measurement, any component. Taking samples, you've got uncertainties. And so we've got to figure out the control limits to put on these. And then testing all these systems. Physical security and protection systems test theirs on a regular basis, and so does the MCNA aspect. You may test the data that's on your accounting system. You may test the tamper indicating devices. So there are a lot of different components that you will check. Just to give you a simple, you know, if you've got, typically if it's a reactor facility where you get fresh fuel in and then you get spent fuel and then you've got the reactor core or wherever the material is in the reactor, you would typically have 3 what we call material balance areas. And so it makes it a little easier if it's an item facility. I simply gave you 2 on this one to show you that there are materials that are coming in. Typically they're going to go to some storage facility, warehouse. Depending on the attractiveness level, it may have a tremendous amount of security built around it. But the materials are stored, and then they're asked for in the processes. So some pure raw material will go to the processing area. If you look at a large facility, probably this processing MBA may be 5 or 6 MBAs in reality. It may be some part of it dissolving it and collecting it in tanks. It may be that you've got to draw a balance around that before you send it to the next phase. It may be going to precipitate it and make oxide out of it. But in essence, you've got material that will go to processing, and you will break it down in MBAs, however it takes to get the right amount of control and accounting on it. And so material then may be a pure product that is shipped. It may be waste, or it may be it's going to go back to the storage facility. So this is a simple one, but in the larger the facility you've got, many more transactions and activities and transfers are going on. But you've got to have all the material that's identified. It's going to be an item or it's going to be in a container. If it's bulk material, it may be in a tank. It may be in an oxide batch someplace. So you're still going to give it an identity when you take inventory. You've got to have it surrounded so that you can measure it, and if necessary, take samples and have those measured and let it reflect what the concentrations are of the materials that you have to account for. But you have to have all materials identified and a value that's defensible assigned to them. You've got to have it all located. It's within an MBA. You've got to have all of your material in your inventory for that MBA identified, and it's where it's supposed to be. Transfers, once it crosses the boundary of a material balance area, you've got to have, again, it's got to be on a measured value. If you've changed it, you've got to get new values for it. But you will transfer it on a measured value and go to another area, and then they will start their book inventory on what you transferred. Again, like we talked about, you've got to shut these operations down sometime. You can't take inventory if it's not in a form that you can identify and measure. You've got to process to the point that you do have an identifiable batch that you can now assign concentration values to, mass values to, so that you can calculate it. So in some form or fashion, you're going to shut down and take inventory. And you're probably going to have discrepancies. I put here significant discrepancies and anomalies. The reason I say that is usually the first time, if you've got a large complex facility, you take inventory, this can't be right. You know, so you get a certain amount of time to prove it can't be right. if in essence, after a little bit of processing and looking at the data, and there are time limits, whether it's hours or a day, you've got to now report that to DOE as a potential anomaly, an incident. But most of the times, you know, there's enough activity going on with taking inventory, you'll resolve these discrepancies. But if you don't, there are limits that are defined as to when you will notify DOE, what kind of response you now give it, what kind of investigation, and how soon you have to resolve the situation. Of course, with all the other parts of the system that are in a nuclear facility, if someone has actually taken something, hopefully you had other components. Gates were crashed, doors were crashed, the PIDUS system that's around it, you had alarms. But all of those together have to work to resolve whatever the situation is. Primary accounting control indicators, yeah, first thing is if you go out there and an item's missing, you got to do something right quick. I've got something, I don't know where it is. So you're going to respond right quick if you got a missing item. Next is what we talked about, the inventory difference. We're looking at, again, loss or gain. You know, most time we say, if I've lost something, I'm in bad shape. Well, if you gain too much, you're in bad shape too. How could you gain that much? Where did it get lost that you gained it from? You know, so there's all kinds of potential for gain as well as a loss. If it exceeds the limits, then you got to respond the same way. Sure, I'm kind of more concerned if I got a loss right now, but hey, we got to look at it the same. Statistically, it's significant. So you look at the book inventory and the physical inventory. The difference between them is where the inventory difference comes in. To break it down just a little bit more, you could say that you've got a beginning inventory. That's on the book. I get receipts. Material comes into me. I've got to add that to the book. I got material that I ship. I got to subtract that from the book. And then I'm going to take an inventory somewhere along the line. Now, it may be that that inventory was changing on shipments and receipts for 2 months, but I've updated all my records. But now when I take the physical inventory, I'm going to subtract from that adjusted book and see what my inventory difference is. And if it's outside the limits that have been established, then we'll respond accordingly. And all of that's detailed as to what type of response you're going to give it. And then the same thing with shipper-receiver differences. There are defined measurements by the shipper and by the receiver. And in essence, you would compare your value for all of the material and the uncertainty around it with their value with all the uncertainty around it, and see if the combined limits of error of those and the difference you've got is significant. If so, then you've got another response. You've got 2 sites involved this time, and it can get pretty significant if you have a difference between 2 facilities that are 1,000 miles apart. This is a fairly simple equation. These can be extremely complex because we're talking about samples that have uncertainties. We may have hundreds of samples in an inventory period. We're talking about maybe 7 or 8 different analytical techniques, mass spectrometry for isotopic analysis, X-ray for maybe the elemental analysis. Maybe NDA has come into play, and that's the best way to do it. All of those measurements have uncertainties built around them. Anytime you weigh something, you can't weigh it exactly. It may be 10 kgs, but maybe it's plus or minus a few grams because the scale is not any better than that. So you don't ignore that. You say, well, that's close enough, yeah. But you still got to put all of those uncertainties into this statistical model that will tell you for this inventory and the active inventory that you had and all the measurements that were made and all the samples taken, it's good to plus or minus this amount. Those typically are pretty tight. When I grew up with MCNA at Y12, we were just changing from what we called historical limits to statistical error propagation or propagation of variance. That's another one. People like not to say, I don't want to propagate errors. Well, okay, variance propagation, however you want to term it. You roll all of those components together, and they were always tighter than what if you take 12 months that you take inventory and you have your inventory difference that's calculated, you can do a statistical analysis on that. My inventory difference is 2 kgs plus or minus this based on my historical data. And that's basically what most of the sites grew up with in the 60s, 70s, and then the 80s started using propagation of variance. And usually the historical limits are looser, wider than what the statistical limits are. Some of that because you just can't actually model everything in propagation of variance. There are things, human factors that come into play that you can't model. So DOE requires, yeah, you do both, but you're going to report on statistical limits, but where it is differing from what typically you would see historically, you investigate that and figure out why. That's not an incident report. It's only an incident report if you exceed your ID based on the accepted limits. But it's not a simple thing, and so that's why we have a lot of statistical folks in the MCNA programs. So if you like math, it's a good field to get into. Typical measurement techniques, certainly the mass, whatever scales or balances that you use to weigh with, whatever volume measurements that you're making. Maybe they're large tanks. In most cases, you can't think of tanks and nuclear materials as being a big bulge tank. You've got to have criticality safety involved, so you're going to have engineering comes to play, but you may have hundreds and hundreds of liters in a large pipe-type tank. And so you've got to know that volume. You've got to know when it's full or how much are you, in essence, measuring the field level. How do you come up with that volume? So there are volume measurements. And then you may have density measurements that come into play, solution samples that are taken that you have to make corrections on, even the materials themselves sometimes. The typical destructive analysis that you get into would be gravimetric analysis, typically converting to oxides and calculating uranium or plutonium in these materials. Titration techniques, which are very precise and accurate. Some of these are used for establishing standards. The New Brunswick Laboratory, which is DOE standard, fabrication laboratory, uses titration to establish the elemental values on their standards. There are a lot of different spectrophotometric methods that are used. X-ray, inductively coupled plasma, even colorimetry is still used in some places. A lot of the old UV visible spectrophotometers may be used for low-level materials. Radiometric techniques, various counting techniques like we've been talking about, may also be employed in process lines to get values for some of these. Mass spectrometry is typically the way that you will certify or establish the values for whatever the isotopes are. U-235 being the one that's predominantly of interest in the uranium fuel cycle. And so you get typically several different isotopes that you're taking and ratioing, but mass spectrometry for uranium and plutonium are the ways to establish the isotopic content. And there are ways, too, that you can spike samples on mass spectrometry to get the elemental analysis as well as the isotopic analysis. And with mass spec, you can save a lot of waste solutions if you can get both determinations with the same method and extremely precise and accurate. Then a lot of the non-destructive analysis that have come into use. It may be that your process doesn't allow you to sample as well as you can measure with non-destructive analysis intact for that container. Sometimes sampling error can be the largest component that goes into accounting for the U-235 in a container. And it may be that gamma spectrometry or neutron counting is the best way to get your overall accounting value on these containers. And then with plutonium and some other materials, calorimetry is used for determining the amount of material in it. These are just some snapshots showing sampling in a box. You've got to have defined sampling techniques because all of the uncertainties in how you sample are going to come to play. And you want that material that you've taken as a sample to represent the container that you're going to apply it to. Underneath that one, you'll see Davies Gray titration technique. That's typically used for high precision determination of uranium in solutions or solids. And then to the right, that's used to be Triton. It's mass spectrometer. Finnegan used to make those, but Thermo Fisher bought Finnegan out. So Thermo Fisher is probably one of the world's leading mass spectrometer manufacturers. I know that we've helped the Russians and other countries, in essence, deal with acquiring these and or exchange samples or establishing values for their materials and standards. Some of the NDA techniques that you'll see used, those of you know Steve Smith, he retired on us, but hopefully we're going to get him back to do some work with us. He worked many years at Y12 and ORNL and invented a lot of different exchange programs with other countries as well. Hold-up measurement, he's outstanding with that, and you can see some of that to the right there the instrument he's looking at is an active well coincidence counter, in which it can measure the quantity of U-235 in the actual can or container that you put into it. To the right, you can see, if you picture a processing facility and pipes and ducts, you can see how large some of the ducts are. And you're like to say, well, goodness, I can't measure that. Well, if you don't include the quantity that's in that duct, even after you've cleaned it out as best you can, there's something, that's tenaciously holding on to the inner surface of that. So there are techniques to estimate the grams of U-235 and uranium that are inside process equipment. Sometimes glove boxes, sometimes solution tanks, but so there are a lot of different ways that we've had to count for all of the materials when taking inventory. Below that, you'll see, you may be familiar with the Canberra UPU inspector. It's good for checking enrichments on containers. Certainly when you're transferring materials and you know what enrichment it was, you should come back within a fairly tight uncertainty with that as to, yes, I've confirmed it. On the bottom there, you'll see what's a device that can handle large drums, 55-gallon drums of waste. And even though it's very low quantities, you can determine the gram quantities in some of these materials. You certainly have to control how it's packed and the standards that you calibrate with. But there are, again, many ways that we try to make sure we account for all the grams associated with uranium processing and wastes and disposals. Talk a little bit about, you talk about material control and accounting. There's that control aspect. There are a lot of different systems, and again, a lot of these are integrated with physical security systems. But the access controls, they're spelled out and defined in your MCNA plan, and they're required under the MCNA directives, but it may be an integrated approach as to how these are put into place and are used. But you've got material access controls, who can get in. The closer you get to a target of concern, fewer and fewer people should have access. And those that have access have got to be approved, certified, and probably on personnel assurance program that they are, no threat, no concern. So there are a lot of different ways that you control access. Data access. I mean, you've got a system that's probably a classified system. You want limited access. First of all, as to who can enter data, then who can get at the network that might misconstrue the data or bleed data off or cause some problem. Equipment access, not only from the standpoint of some of the equipment we showed there, we don't want them cutting open a pipe and diverting some. We don't want them to get at sensitive instruments that are making some of these measurements. So there's a lot of different access controls that may be spelled out. We talked a little bit about the material surveillance and multiple person rules, CCTV, maybe other mechanisms. Tags are getting used a lot now for tracking materials as they're moved around. Material containment. And kind of mentioned that. Usually your fence is your limited area. You can't get into a site because there's controlled access at the fence. Then you get into maybe a higher sensitive area that has another fence that has a lot of more detectors and space built between it. So you'll hear PIDUS, perimeter intrusion detection systems. So you'll have a protected area that has a much more secure fence, fewer people getting into that. Then you'll have a material access area. Very specific operations are going on in this one. There may be several buildings inside this protected area. You can't have free movement between this material access area and the other material access area. Fewer people into each one of those. Then to get at a storage vault in some way or another that it's in a cage or controlled. It's contained and you got the access control for that. Then there may be processing containment so that you don't want people getting at these. A lot of different detection assessments. Certainly TIDs are one that are used tremendously in the accounting systems. They're mechanical sometimes, cables, that if someone gets into the container, they've had to break it open and that's identifiable. It may be an electronic tamper indicating device that will alarm as soon as somebody tries to do something. You got the portal monitors, like with the airport when you walk through the metal detectors. You will have not only metal being detected, you'll have radiation being detected, and the portal monitoring that we have. Someone has radioactive material, you think, well, okay, all we need is radiation detectors. Well, what if they shielded it in lead? Okay, we need a metal detector too. So you have more built into it to try to pick up on someone going out with material on them. Waste monitoring. You may have pipes or streams that are coming out of an area that has nuclear material, and you want to be able to say, yes, I know what's coming out. We sample it, we measure it, we control it. The pipes go here. And then if there's a lot of activity going on, you shut down for the day. It may be that it's necessary to have some sort of administrative check every day that things are where they should be before you totally shut down, close it up, and make it secure. So there may be different ways, depending on the material and operations, what the administrative checks are. And various other mechanisms that you may get into that between you and the DOE requirements and inspections and identity of difficulties, what you build into it to make sure it's protected. This is just kind of I borrowed this from one of the guys out at PNNL. I thought it was a pretty good chart. It kind of shows the overall integration of MCNA with the other systems. You can see that the most sensitive material is in a vault. Then it's inside a building. It's a material access area. Then that's inside that protected area fence. Then that's inside the limited area fence. So each one of those, as you get closer and closer to the target, more controls, fewer people, so that all of these things are working together. You can see on the bottom that it's just kind of giving you, again, a lot of the components that may make it up. Portal monitoring to get in and out, TIDs, waste monitoring, data administrative checks. So a lot of the different things that we've talked about, all of it has to roll together, be integrated and working to make sure you got the protection system necessary. Potential results if you don't have a good MCNA system. Certainly undiscovered diversion or theft. When we say diversion, it may be it's not where it's supposed to be. Someone has located it somewhere else in this MBA or in this MAA, waiting for the opportunity when an alarm or a door gets evacuated to run out with it. So you want to know if it's diverted, if it's been relocated somewhere in that processing area, just in case. Then it's certainly theft, whether it's grab and run or steal, or by diverting over a long period of time and get a significant quantity. Unexplained loss. If we, in essence, come up with a inventory difference that's a loss, that's large, and we can't explain it, we've got problems. I have dealt with a lot of inventory differences over the year, but thank goodness we've been able to explain them. But you do spend a lot of time getting to that point sometimes, and there are times we had to report to DOE, and it may drag out for a while. We get a lot more help in trying to resolve it, but eventually you'll come up with an investigation that's extensive enough and has all of the input and people looking at it that you've satisfied what's necessary. Poor criticality safety. A lot of the times these processing areas only know to a great degree what's there based on the accounting system. And so there are a lot of different controls that are built to make sure we don't have a criticality incident. And that's probably one of the things that will shut down a facility forever if we had that. In the early days we did, 40s, 50s, and 60s, we had criticalities. But every time that happened, then you learn more, you build more, and the MCNA system does help. Poor environmental stewardship. These are, sensitive materials for a lot of reasons, and if they get out to the environment, they can cause a lot of potential impact on the population as well as the environment itself. And so having a good MCNA system helps keep track of that as well. You don't want to have too many false responses. If you've got a system that your statistical limits are too tight and all you're doing is getting responses, you haven't defined it well enough. And so you need to work on that. You don't want too many false responses. But you don't want to never have a false response, or you got it too loose. So you got to find the right balance in responding and fixing the situation. If you don't have a good MCNA system, you can have shutdown of operations in facilities. And I've seen stand downs and I've seen various things because of where is it. Loss of credibility. If you have that to happen enough, then you're probably going to lose it. You won't be the contractor for one of these sites. There may be a lot of other things that may come into play if you don't have the credibility or at least confidence of Congress as well as the area where you live, and certainly the DOE who is sponsoring. We don't want the potential to not know well enough where it is that someone could be a terrorist that is going to try to make off with material. We want to certainly prevent that from happening. We don't want to have that kind of vulnerability. And if you do lose, then you got the potential for international nuclear threat. That's one of the reasons we've tried to help so many countries who are not, say, as developed in a lot of these systems as we were, to help get there, so that they are keeping track of their materials and it's not a threat to others around the world. So let me summarize. A lot of the control and accounting started in the 40s with nuclear material creation. Nuclear material being the ones that we're talking about in the weapons cycle and the power use cycle. And it was a lot based on financial accounting. Certainly the needs and capabilities changed, sensitivities to these materials, and the number of people who had these materials and countries who had these materials. Accounting evolved from, I know, first time I went into MCNA, a lot of the bean counters are still there. Referred to them just like you would an accountant in a bank. They can count the pennies. Well, it's not that simple. So you went from manual systems to near real-time computer systems, and a lot of data processing, format, tracking. How can you break it down to tell you what you need? A lot of new techniques have certainly come along the line in both destructive analysis and non-destructive analysis. The SEALs and TIDs and electronic tagging and things that we use now. Surveillance systems and the layers that we have of it, multiple surveillance of things that are going on. Process monitoring is a way to identify before you get an inventory difference if you've got something that may be not giving you the amount that you thought at some particular process point. So a lot of sites are building process monitoring into it before they ever take physical inventory to be able to respond. And all of the controls and support systems. So MCNA, if you ever had an interest in it, it uses a wide range of professionals. Accountants, engineers, scientists, statisticians, administrators. And certainly as we've showed you just a lot of the different analytical measurement methods that are used. A lot of specialized training nowadays. It's like everything. You're going to specialize in probably a small part of it nowadays, but really get good at it and give the system what it needs. This one, dedicated, understanding, thick skin. You get a lot of inspections in this arena, and you got to be able to not get upset and be able to defend it and be able to accept when it's not what it should be, and you're going to make it better. So you got to be politically savvy, I think, because a lot of these inspectors may be from different accounting, maybe the GAO, accounting office, it may be the Inspector General's office. You're going to have regular DOE inspections. So you got to be willing to deal with that. And then of course, international threats and international cooperation has increased significantly, and thank goodness they have, because it's amazing how much folks have gotten involved, how many countries are willing to sign up and keep track of the materials the right way, how many of them are willing to donate very sensitive materials and settle for LEU instead of HEU with some of their research work. So there's a lot of different aspects of it. I don't know that you need any additional slides, but there's just a few, well, just a few examples if you're interested. This was back around 2002 when the Venture Institute in Serbia was willing to give up, and so a lot of negotiations got started, and they were the first in essence, country to send back a lot of their highly enriched uranium to Russia, repatriated that material. And so I was lucky enough to be on that first return and got to work with a lot of the IAEA folks as well as the Serbian and the Venture Institute folks and a lot of the Russian folks. But you can see a lot of the different components of MCNA being used. The NDA, that's a fuel element that you'll see on top of that little orange stand there. It had about 10 grams of high enriched uranium in it, and there were probably about 6,000 of these that made up the research fuel at that site. And so random samples taken to check them to see that they were as the book indicated they were. And then all of these were loaded under a lot of surveillance by a lot of different countries in this particular case into the containers that you see there. And they put several TIDs across the top of those to make sure that they, in essence, were secure. Material was then shipped and loaded on a plane. And so there was, again, it was at night, and it's amazing the convoys that went in other directions didn't have material, and the convoy that went to the airport that had the material with it, and all of the protection systems built along the way to make sure that that material didn't get lost. That's me on the right there. We were able to get on the plane too and actually check the containers. Yep, that's the same ones we shipped. I've checked them all again because it was leaving here, flying back to Russia after it left Belgrade, Yugoslavia at the time. Now it's just down to Serbia. So that was in 2002 that was all shipped back to Russia. All of that material has been down-blended to LEU now. And that's gone on with a lot of the programs that you see for all of the research reactor sites, part of the original Soviet Union, and then part of them that the Soviet Union provided materials to at that time. So there's been a lot of material that's been sent back to Russia and converted. That's under another major program that works with them to get that to happen. But a lot of MCNA parts of it that go into it to make sure it's okay. This was one other site that gave up all of their highly enriched uranium in Russia itself. Krylov Shipbuilding Research Institute in St. Petersburg was willing to give up all of their HEU, and it was sent to one of the sites for the projects that I work on where we downblend material, and I get to monitor a lot of that work. So again, weighing TIDs, and then using NDA to check the enrichment on it again, and then all of this highly enriched uranium, in essence, has been downblended. Any questions?